this is this talk is about the simplest two-sided matching model, namely the marriage game. So, by the way, this is recent work with Kemal Yildiz from Bilkent University, who is currently at Princeton University. And yes, so it's about a two-sided matching market where we have agents on each side, an equal number with no loss of generality. And the interaction is each agent on one side is interested in finding a mate, matching with a mate on the other side. So a one-to-one map is called a matching. Now, the input of this game, of the problem, is a preference profile. Each agent has a strict ordering on agents on the opposite side. So let's refer to them as boys and girls. By the way, our work here is generalizable to a certain extent to many-to-many matchings, but I will talk purely about one-to-one matching here. The solution concept is a stable matching. Okay, that corresponds, by the way, to the core of this game when viewed as a cooperative game. And a marriage or a matching is stable if there is no man-woman pair who prefer each other to the mates they are matched with at mu. Stable matchings exist, famously known by the Gale-Shapley paper and algorithm dating from 1962, famously again as found by the so-called deferred acceptance algorithm or procedure. Our starting point is to view the entire set of stable matchings. And typically, there exist many stable matchings. In fact, there is a very nice orderliness in this set of stable matchings. So let us say that a matching is man-wise better than another matching if either for each man, either he gets the same mate in the other matching, or his current mate he prefers to his mate in the other matching. Okay, and typically it may be the case that one matching man-wise dominates another matching, but typically when we have two matchings, they are typically incomparable. Some men prefer one, other men prefer the other matching. Okay, so a very early fundamental fact is that the set of stable matchings under this relation, man-wise comparison, forms a lattice. Okay, so let me be more precise about this. If we take any two stable matchings, then they have a precise least upper bound, very concretely found in the following way. Ask every man which of the two mates he prefers between these two matchings. It is a fact that when you do this, no two men will point at the same woman. This is a consequence of stability. Thus, this generates a new matching, one-to-one matching. And it turns out that when we do this, when we give each man his more preferred mate between these two matchings, we get a new matching, and that is stable. So that we can call the join of these two matchings, or the supremum, the least upper bound in this ordering, etc. Likewise, there is an infimum if you go the other way and give each man the less preferred mate. Okay, so this fact was observed by Conway and spoken a lot about by Knuth. Okay, let me give a concrete example here, which I will refer to later on. In this example, we are seeing 6 men, 6 women, men 1 through 6, women A through F. And here you don't have to look at the numbers, but they are the rankings. The numbers below the diagonal, the black ones, give the rankings of the men over the women, and the red ones of the women over the men. Okay. Now, we have here, what we're seeing is the lattice of stable matchings of this particular example, of this profile. Just to go over that, I will come back to this later on. And here, this gives me the opportunity to mention a very important property of the lattice, namely polarity. So if we take any two matchings, for example, this one that over which it's written 2, 2, 1, 1, 1, 1, that means that in this particular matching, the first 2 men are getting their second best women, and the other 4 men are getting their first best. Okay, so it's this particular matching. And if I take this other matching on the right below, I see that the first 2 men are getting their first best, and the others are getting their second best. Now, they are incomparable, these 2 matchings, but their least upper bound is the top one, where everyone is getting their first best. Okay, so here we are seeing only the preference evaluations of the men. I could have recorded here, which I didn't because it would be crowding, the preference evaluations of the women at these matchings. And the top one, for example, where every man is getting their first best, the women are getting their 6th best, or the worst candidate. So in fact, if I take any 2 matchings and look at their supremum, that supremum is at the same time the infimum according to the women's preferences. So there is this opposition of preference achievement as we move through the lattice, and that they briefly refer to as the polarity property. Okay. Now, the motivation of this work is to delve into an exploration that is not undertaken by the matching literature, which has been very active, especially in the last 40 years, and has been given a market design Nobel Prize award. But the focus has been almost exclusively on these extremal matchings, or the man optimal, at the same time the women in female, and the other one, the man in female, women optimal, these extremal matchings. And there are two reasons for that. One reason is that these extremal matchings enjoy a strategy proofness property. Namely, if one knows the preferences of the women, for example, and one were to elicit the preferences of the men with the formula that then the man optimal matching will be computed, then no individual man, no man can benefit from misrepresentation of his preferences. Okay, so this is a very strong result, but two things about that. It's a strong assumption that the preferences of the women are at hand, but beyond that, it is unfair, because what is being, even if you know the preferences of the women, the targeted allocation is male optimal, and it's the worst for the women. So this has been ignored entirely. Why is a good question. And there are, the main reason for that is that it is very challenging to conceptually define what could be in the middle. By the way, given the polarity property, it is intuitive that one, in the name of equitability or fairness, one would like to be somewhere in the middle. If the male optimal is the North Pole and the women optimal is the South Pole, then you would like to find a matching at the equator, sort of. That's a sound idea, a good idea, but when you try to pinpoint what may be the conceptual underpinning of such an idea, it turns out to be very elusive, and no sound criteria, it's not successful to go in that, it hasn't been successful to go in that direction. Okay. So a second reason, and I would like to mention that here at this point, is that the number of stable matchings is not polynomially bounded by n, the number of men equal women. So it's a complexity problem. If one asks to list the set of all stable matchings, then this is an NP-hard problem. So that stands as a side issue, this complexity issue. And then if it's complex to list the set of all stable matchings, then computationally, how can you aim to find a matching in the middle, even if you were to conceptualize it in a sound way? Okay. So our aim here is to introduce a framework that is able to do this. Okay. I would like to use the word matching rule, which a matching rule pi associates each matching problem with a subset of matchings. Okay. And a stable matching rule picks up stable matchings. Okay. And we would like a stable matching rule to obey this minimal condition called invariance under stability. It's possible that two problems with different preference profiles may have exactly the same set of stable matchings. In that case, our stable matching rule should find the same solution for both. Okay, so a matching rule is a stable matching rule if it satisfies stability. In other words, if it picks up only stable matchings and if it obeys invariance under stability. Now, quickly, the literature, as I suggested, is quite, there's not much there. We can, I can mention them, what exists in the literature in two categories. The ones on the right do not satisfy invariance under stability. For example, the last condition that I mentioned. By the way, these, let me read one of egalitarian stable matchings, for example, from 1971. What it aims to, the definition of an egalitarian stable matching is at each matching, you record the rank achieved by every agent, man and woman, and you just sum these up, and then you go for the minimum, the matching that achieves the minimum total rank. So the lower the rank, the better off that agent is. The solution of this optimization exercise gives us the so-called egalitarian stable matching, for example. It's an example of an attempt which fails this invariance under stability condition. The bottom one, on the red one, sex equals stable matching. That's similar, but in spirit, but different. It aims to minimize, it first of all computes the total rank achieved by the male side and the female side, and minimizes the difference between these two sums, and that's given the name sex equal matchings. That also violates invariance under stability. The main reason that here for intuitively is that, for example, Elena may be my first best, but I may not be able to match with Elena in any stable matching if it is not quite normally the case that she is not interested in me. So that means I'm not able to achieve my first best, but that's going to enter into these computations. Sex equals stable matching, egalitarian stable matching. That's the simple reason behind why these matchings, by the way, these have been mostly been explored by computer scientists. Why they disobey this condition that's appealing. The ones on the left, let me briefly refer to them. I don't want to lose time, but the top one, called the median stable matching, is a very interesting one. And it, by Theo and Seturaman, the definition of a median stable matching is that you order somehow all stable matchings from 1 to whatever the number, total number of stable matchings is. It is possible to order all these stable matchings in such a way that there's a certain monotonicity in the achievement of the individual agents, and then you go for the median. That's the definition in this order. That's the definition of the median stable matching, and it enjoys the property that the median stable matching, in fact, gives the median to each individual. But there, the median is counted in a particular way. Okay. Now, our starting point is that, as I mentioned a little while ago, if I'm not matched to Elena in any stable matching, then she is by definition unattainable for me. So what we do in this paper is restrict attention to attainable ones. Okay. In the example above, it's a symmetric, it's a specially concocted example. For each woman, her second best candidate is unattainable, it turns out. Okay? And for each man, his sixth bottom candidate is unattainable. So in that particular example, each agent, it's a very symmetrically concocted example, I will refer to it later on, each agent has 5 attainable mates. Okay. Now, so as I mentioned, the egalitarian stable matching, this one is, we can be very critical about that because it doesn't obey invariance under stability. But in the same spirit, we can do the rank achievements among the attainable ones, restrict ranking to among the attainable ones. So if Elena is unattainable to me, my first best doesn't count, okay? But it turns out, cynical, in a cynical way, that if I were to minimize this objective function, then I don't get anything because this sum is constant among all stable matchings, every element of the lattice. Okay. Now, the title of the talk is Equitable Stable Matchings under Modular Assessment. Okay. And I'll be presenting 2 theorems. One of the theorems uses this keyword modularity, modular assessment, and it is of a mathematical nature. We regard it as the more significant finding in our paper. That's going to be theorem 1, and then we will apply it in theorem 2, and to be for the location of for this conceptual finding for undertaking equitability among stable matchings. Okay. Now, an assessment function is simply a function on the set of stable matchings, which attaches a fairness loss index to each stable matching. So view this as a numerical function on the lattice. And a modularity, and this function is said to be modular if this identity holds, namely, if the assessment of a matching mu plus a matching mu prime is equal to the sum of the assessments of their supremum and their infimum. Okay, so if this is a critical knife-edge criterion, and submodularity, supramodularity plays a big role in optimization. But our paper is restricted to modularity, and I will be boastful about it. Okay, this is going to be the content of theorem 1. Okay, so let's call a stable matching rule, an apparatus that we have, which whenever we are given a stable matching problem, it picks up a subset of the set of stable matchings of the lattice. Let's call that such a stable matching rule modular if it can be gotten by minimizing a modular assessment function. Okay. If for each problem, the solution set is the minimizer among all stable matchings of a function f that is modular over the set of stable matchings. Okay. Now, is it maybe not immediately intuitive, but here's a very simple result to prove proposition 1, not theorem 1. It turns out that in the matching story, a function over the set of stable matchings is modular if and only if it can be decomposed into, if and only if it can be, it's the summation of individual assessment functions. Okay, f versus f sub I. So f sub I is how the achievement of agent I is assessed. By the way, this assessment is understood to be being done by a socially minded center or decision maker. Okay. Okay, this is the social value of a stable matching is obtained by adding the individual assessments for each agent. Okay. Now, somewhat important but side remark here, it follows from the optimization literature going back to 76 that minimizing, optimizing a modular function is equivalent to the problem of finding the min cuts of a specific flow network. Why is this significant? Because it is a polynomially bounded algorithm. Okay, remember the set of stable matchings, the number of stable matchings can be exponential, not bounded by a polynomial, but our result will refer to an algorithm to find equitable stable matchings that will have a nice convergence property. Okay, it will be polynomially bounded. Okay, here's our theorem 1. A stable matching rule is modular if and only if it satisfies convexity. Now, at this point, you're probably wondering, what is convexity? We have been challenged by finding a word. We are not too happy by this word convexity, and I will show you that this does not have that much to do with what is typically understood by convexity. So I'm going to take a few minutes to explain convexity. But let me read this theorem. It says that if a matching rule is modular, in other words, if it can be gotten by minimizing a modular function, then the solution set has this property called convexity. Okay. In the other direction, pick any subset of the lattice. If it has this property, convexity, then there is a modular assessment function which would generate it. Okay. The point before I illustrate this condition convexity is that it is a very minimal condition. Okay? It's a minimal concession. So for us, this theorem is saying that essentially any stable matching rule with this proviso of respecting convexity can be gotten by a modular assessment. Okay. And why is this nice? One, as I showed in the previous slide, because it has this polynomially boundedness property as an optimization algorithm. Two, because okay, I will comment on the other aspect, why it is significant. Okay, so what is convexity? This is the definition of convexity in the matching context. We have an equivalent theorem for abstract lattices. But in the matching context, suppose we have a matching rule, and there we have two elements in the stable matching rule, mu prime and mu double prime. Okay. Now take any agent, any man, and look at the two mates that he has in these two matchings. Okay. If there is a stable matching where this man is getting one of these two mates, and if this is true for every m, then we call this matching rule convex. It satisfies convexity. Okay. So it is not immediately so easy to grasp what this is saying, but let's look at this example of a lattice, okay, with what we have 6 stable matchings here. The one at the top, every man is getting his first best. The one at the bottom, every man is getting his fourth best. And there's a diamond in the middle that I need not put into words, okay? So there are 6 stable matchings. Now, convexity says that if you look at these 2 stable matchings, if our rule picks up these 2, where every man is getting his second best and third best, then our matching rule should pick up the entire diamond, okay, the other 2 as well. So that is in keeping with what one expects from this word convexity, okay? However, look at this one, okay? Look at these 2 red matchings. Every man is getting his first best, and the first 2 second best, and the last 2 third best, okay? Now, there is no mixture of these 2 red matchings, which is stable, okay? So this subset of 2 consisting of these 2 stable matchings satisfies convexity. It does not have to include this other matching where everyone gets his second best. It does not require that. So I think this illustrates how quite general, how unassuming this condition is. Also, for example, it's possible that a stable matching rule may pick up the top one and the bottom one. Okay, there is no matching where every individual gets either his first, every man gets either his first best or fourth best. So convexity holds again vacuously. So in other words, this condition is not imposing. Okay. Okay, so before I move on, let me see, how much time do I have, Fuad? Hello? Hello?
Sorry, I switch on the microphone. So,
can you hear me?
Yes, yeah. Can you hear me?
Yes, I can hear you now. Okay.
So you have something like 15 minutes.
Okay. Okay, so this is our main theorem, mathematical result, and in one direction it is straightforward. If a stable matching rule is modular, then it satisfies convexity. But in the other direction, pick any subset of the lattice. If it has this property, then it can be obtained by minimizing a modular assessment function. That has been the challenging part. In fact, this condition, convexity, has not appeared in the literature before. So it is we have also perused it in the lattice literature. There is no analog of that in that literature as well. Okay, so now let me move on to equitability, fairness, and I will conclude with our second theorem. Please, let's look at this example, the profile of which we looked at in the beginning. There we were only seeing men's achievements, but here we have also included the women's rank achievements as well in red. And let me ask you, if you are following this picture, you know, the man optimal matching gives every man his first best among attainable ones. And at the other extreme, the women optimal matching gives every woman her first best, but the fifth best of every man. Okay, first best, fifth best. And we have this at the top, these diamonds, these other combination of matchings to the right and to the left. So let's ask ourselves, in the name of equitability, which among these matchings would we recommend? Well, it turns out the median stable matching that we were critical of, in fact, picks up the matching where every man gets his second best and where every woman gets his fourth best. And clearly that is, this example is so specially concocted that it is obvious that this is unfair. Okay, why? Because there is a matching where every man and woman gets her third best, which is his or her median stable matching. That's the one in the middle. In this case, there is unequivocally, there is a matching where every agent gets his median or middle candidate. But the median stable matching misses that. Okay, so in fact, we can define for each individual now, not for the stable matching, but for each individual, consider the mates of an agent that have median rank. There can be a tie if there's an even number of attainable mates. In that case, we pick the one that he prefers more. Okay. Now here's an example of what we would call an equitable stable matching. Okay. So for each agent I, take any matching and any agent and record the rank achievement of that agent with his or her mate, and subtract from that the rank of his or her median mate. In other words, measure the rank distance in rank between his or her achievement and his or her median mate. If he or she is getting the median mate, then this difference is 0. But otherwise, take the absolute value of this difference and take the sum over all agents and minimize this function. Okay, we call this minimizing total spread from attainable median. And this is an example of a modular stable matching rule. Okay, now getting close to concluding, here we have a simple intuitive notion of fairness that we call equity on dominance. Okay, we would like to pick a stable matching that satisfies this criterion. But typically there will be many that fulfills this condition. So what does equity on dominance say? So a matching would fail to satisfy equity on dominance, would be equity dominated if it is possible to move from that matching to another matching where every agent is closer to his or her median mate. Okay. Otherwise, if this is not possible, we call that matching satisfying equity on dominance. Okay. Now, just very briefly, here's an example with 8 men and 8 women that we enjoyed working on, and this is the lattice of that matching. It illustrates several things. There are 6 stable matchings, 3 at the top, 3 to the left, on the left side. There are 6 matchings here that satisfy equity on dominance. All the others are equity dominated. Okay, and among these, this blue one, turns out to be the matching that satisfies, that has minimum total spread from the median. Okay. Now, as I said, the second theorem is an application of the first theorem. So again, it's a characterization, and it says that take any stable matching rule and suppose it satisfies it satisfies convexity, as in theorem 1, plus equity on dominance, if and only if it can be gotten as the minimizer of an assessment, of a modular assessment function, which we know from proposition 1 decomposes into individual assessment functions, but where, the bottom line, each individual assessment function is single-peaked or unimodal with mode median I, okay? So if we were to read this in both directions, as I remarked before, convexity is a minimal concession, and equity on dominance is a sound fairness notion, then we can satisfy these two conditions as long as we attribute any unimodal assessment function to each individual, to each man, to each woman. And there are so many of these that this result illustrates the breadth of the possibilities. And that's what we meant by providing a framework for this fairness exploration, okay? These individual assessment functions around the median, attainable median, need not be symmetric to each side, can have different slopes. The individuals can be given different weights, one as opposed to the other. So there is a lot of richness that this theorem provides, and it is in the modular class. So it has this polynomially bounded as property as an optimization problem, etc. Okay. Now, I will go over the second bullet here as a main comment. The underlying mathematics of this work rests on the Birkhoff representation theorem for distribution lattices, okay, from 80 years ago, which says that no men, women, or individual agents which are being matched with each other, but if you take any lattice, abstract lattice, if it is distributive, then it has a set of generators called the join irreducible elements of the lattice, and one can generate the entire lattice by operating on these generators. So it turns out that in the matching context, there's a set of rotations, the rotation poset. By the way, this generator poset of Birkhoff, the set of all join irreducible forms a poset, and that generates the entire lattice. So it's it captures the essence of the lattice. By the way, the lattice can be huge in number, and this poset much fewer in cardinality. And this we see in the matching, stable matching lattice. It turns out that in one-to-one matching, the stable matching lattice is distributive. So the Birkhoff representation theorem works here. And our contribution here, as I mentioned before, is this modular picking any subset of the lattice and recovering it as a minimization of a modular assessment function over the lattice is possible if that subset enjoys this property that we called convexity. And it turns out we have looked across the lattice literature, and that doesn't seem to, we have not found a reference to it anywhere. Okay. Okay, I mentioned in the beginning that the marriage, the one-to-one matching problem is quite particular. Many-to-one, many-to-many matchings are have a lot of applications and are more general. And it turns out that there are conditions on the choice functions there that ensure that the set of stable matchings is a lattice, but a distributive lattice. And then our results here would generalize to that context. Okay. Fuad, I'm done.
Great, great. You see, I enjoyed it enormously. Thank you very much indeed. Yeah.
I wish I could, I wish I was making gestures. I wish I could be seen, but
no,
that was an accident. Okay.
But it is really, really very, very interesting. And what is interesting also that in this case, you in fact reduce the problem of, in a sense, to find a fair matching to the simple optimizational problem. This is really something very good. Is it published? Has it been published?
We have submitted it and are waiting for a response.
I see. I see. Very good.
Yeah.
Congratulations, Ahmet.
Thank you.
Please, dear colleagues and friends, please ask questions. That is, let me ask maybe a question, you see. It's very interesting that for so many years, you see, from 61, 62, in fact, you see, first article by Gale and Shepley, wasn't it published in 56? Something like that. I don't remember exactly, but something those years. You see, this apparatus is used enormously, yes, in schools, etc., etc. I can 10 minutes even just list all these applications, but nobody, in fact, did such kind of analysis, deeper analysis. What does it mean? This how can I say, this opposite distribution for men and women.
Yes.
How it might be resolved in, for instance, this story about opposite distribution, you see, even I do know this, that it is possible to construct such matchings, you see. but nobody did, in fact, really went.
Okay, can you see me now?
Yes, I can see you now.
Okay.
It's really very, very interesting. It's fantastic. Yeah, I enjoy it very much. I enjoy it very much.
Thank you.
Well,
You are kind.
no, it's not kindness. It is really, when I enjoy, I say openly that I enjoy it. It's not a kindness. When it will be published, just send me the material, okay? The article, I will be happy to read it.
Okay, let's see if the editor likes it or the referees.
No, it's very serious work. It's very serious.
Okay, I apologize for the disturbance. In the morning, everything was working, but I couldn't get these to the slides and this connection at the same time. And
it happens sometime. No problem.
Okay.
Okay.
In the end,
yeah.
I could carry it to the conclusion. Yes. Okay. Thank you for listening.
Thank you. Thank you very much. And dear friends and colleagues, we interrupt now until tomorrow, 11 o'clock. At 11 o'clock, we proceed with the program, okay, according to the program. Thank you very much indeed. Have a good evening. Bye-bye.
Bye-bye.